Welcome to Dr. Balga's podcast for the Curious Doc. Today, January 23rd, 2026. This video is on a review published in Cancer Discovery in this month's issue of Cancer Discovery, titled Off Barriers and Loops: How Evolution Limits Most Cancer Risks to Older Ages. Why do most cancers rise sharply with age? Evolution favors tumor-suppressive barriers that mainly protect reproductive years. Aging erodes those barriers and changes tissue environments. What does an evolutionary explanation add beyond mutations? It explains why defenses are calibrated to fitness benefits, not perfection. Cancers are delayed, not eliminated. What is meant by barriers to cancer? Multi-level tumor suppressive mechanisms that block progression from mutant cells to invasive metastatic cancer. Are mutant cells with cancer-associated mutations common in healthy people? Yes. Clonal expansions and pre-malignant changes are widespread, yet most never progress to lethal cancer. Why doesn't natural selection prevent cancer entirely? Selection optimizes reproductive success. Protection after reproduction yields diminishing fitness returns. What is antagonistic pleiotropy? These are traits that improve early life fitness but have late life costs, contributing to aging and age-associated diseases like cancer. How does historic human survival shape cancer timing? If few ancestors lived past age 50, selection pressure to prevent late life cancer was weak. What is somatic evolution in this context? Selection acting on heritable changes within body cells, enabling clonal expansions and rarely malignancy. Why is cancer described as extremely inefficient? Most potentially malignant clones fail due to multiple suppression mechanisms at each step. Which major barrier categories do authors highlight? Genome, epigenome maintenance, regulated cell death, senescence and telomeres, cell competition, immune control, metastatic suppression, and dormancy. Does mutation burden rise faster in old age? Single nucleotide variant accumulation appears roughly linear across lifespan. The risk rises as context and barriers change. What is epigenetic drift and why does it matter? Age-linked disorder in epigenetic marks that increases cellular variability and can favor malignant evolution. Why do larger animals not have vastly more cancer, or Peto's paradox? Across mammals, mutation accumulation per lifespan is constrained. Other evolved defenses also scale with size and longevity. How can endogenous retrotransposons contribute to aging and cancer risk? Their awakening can trigger cytosolic nucleic acid sensing, type 1 interferon responses, and chronic inflammation. What does epigenome maintenance include? DNA repair, genomic stability, and preserving epigenetic patterns that limit harmful heritable variation. What is regulated cell death? Programmed pathways, example the apoptosis, that remove damaged or potentially pre-malignant cells from organismal benefit. How do oncogenes trigger tumor suppression in normal cells? Oncogenic activation can induce apoptosis or other death programs, acting as an early barrier to transformation. Does apoptosis change with aging? Evidence suggests reduced apoptotic sensitivity in aging tissues, weakening this barrier. What does regulated cell death matter for therapy in older patients? Or why does regulated cell death matter for therapy in older patients? Many treatments rely on death pathways. Age-related changes may alter efficacy and toxicity profiles. What is oncogene-induced senescence? A stable growth arrest triggered by oncogenic signaling or DNA damage, often paired with inflammatory secretions. What is senescence-associated secretory phenotype or SASP? It's a mix of cytokines, chemokines, proteases, and vesicles that can reshape microenvironments, sometimes tumor promoting. How can senescence both suppress and promote cancer? It halts proliferation early, but accumulated senescent cells and SASP can foster inflammation, immune suppression, and invasion. How do telomeres function as a barrier? Progressive shortening limits replicative capacity. Critically short telomeres induce senescence or crisis. Why is telomeres tightly regulated in humans? Restricting telomerase after differentiation limits unlimited replication, reducing transformation risk. Why is the telomere cancer a Goldilocks problem? Too short promotes tissue dysfunction. Too long enables mutant clone expansion and transformation. What is cell competition? Fitter winner cells eliminate less fit neighbors, preserving tissue integrity and removing potentially oncogenic cells. How might cell competition decline with age? Aged microenvironments and stem cell functional decline can reduce the ability to eliminate aberrant clones. What is adaptive oncogenesis? Aged or damaged tissues create landscapes where oncogenic phenotypes become more adaptive and thus more selectable. How does immune surveillance act as a barrier? Adaptive and innate immune cells can eliminate or restrain emerging tumors. Cancers evolve immune evasion. Why does inflammation raise cancer risk? Chronic low-grade inflammation can impair immune control and select for clones that thrive under inflammatory stress. This is in a nutshell about this review. Read the article in detail in Cancer Discovery, Jan 2026. Eponyms related to this article include the Hayflick limit, which is replicative ceiling for human diploid cells in vitro, foundational for telomere and senescence biology. Peto's paradox: across species, cancer risk doesn't scale simply with body size or lifespan, implies evolved protective mechanisms. Williams' antagonistic pleiotropy: early life fitness benefits can carry late life costs, framing aging and late life cancer risk. Podcast brought to you by masterbedfacts.com. This podcast is for physicians and healthcare providers. If you enjoyed this video, please like, subscribe, and forward to your friends.